Here at the Micro Nanoscale Thermal Transport Laboratory, we're interested in phenomena that happen at extremely short time scales and extremely short length scales. The way we do that is through something called the pump probe technique. So we have a laser that can create laser pulses as short as hundreds of femtoseconds, and we shoot that pulse into a beam splitter and create two paths. We call it the probe path and the pump path. And by creating a delay in the probe path, we can actually get a time delay between when these two pulses hit our sample. In this case, when our pump hits our sample, it deposits energy in the form of thermal energy, and then the probe comes in with some time delay after that we can control with this delay stage, and then it basically measures how much energy has been dissipated since the pump pulse arrived. And by changing this time delay, we can get a time evolution of how that energy changes, and we can use that to characterize thermal and magnetic properties of different samples. So this is our real setup. Here we have our laser that creates femtosecond pulses, and the pulses come through and follow this path, bounce off two mirrors here and come back, and at this beam splitter here, down here, we have it split into the pump and probe paths. If you see over here, this is our delay stage that introduces the time delay between the pump and probe. And then up here at that beam splitter up there is where the pulses are recombined and sent to the sample. In the case of thermal measurements, what we do is we're measuring the sample's thermal profile directly with the probe pulse. And that gives us information with the time delay about how the temperature profile is changing in time, which gives us information about the thermal properties of our samples. In the case of our magnetic measurements, the case gets a little more interesting. We subject our samples to a strong magnetic field up to 3 Teslas, and then when the pump pulse comes in, it causes the magnetic moment of the sample to begin to oscillate around the external applied magnetic field. And then when the probe pulse comes in, it can measure that oscillation, and the rate of that oscillation and the rate of the damping of that oscillation can be used to characterize the sample's magnetic properties.
Our research group spans many disciplines, from condensed matter physics to electrical engineering, and it has applications in multiple fields: in solid-state energy conversion, thermal management, photonics and solar energy, photothermal dynamics, and data storage. One area of research that shows particular promise is in magnetic storage through heat-assisted magnetic recording. This is a technology whereby the magnetic properties of the recording layer need to be characterized in great detail, which is something our lab is capable of doing. We also have many group activities outside of just research where we get together and have dinners sometimes, and this last year we were lucky enough to spend a few days at a lake up in northern Minnesota.